So, hello everyone. The goal of this video will be to define the vector spaces Rn and Cn. And we do so before giving the general definition of a vector space so that we'll have an example when the definition comes along to orient ourselves by. So before jumping into the actual construction of these spaces, we need to review number systems. So the number systems we'll be using are the natural numbers n, these include numbers like 0, 1, 2, 3, and so on. Then we'll be using the integers, z. So these include the natural numbers like 1, 2, 3, and so on, but also the negative numbers, -1, -2, and so on. Then we'll be using the rational numbers, q, and these are numbers of the form a divided by b, where a is an integer and b is a non-zero natural number. Then we'll be making extensive use of the real numbers r, so these include the rational numbers, but also irrational numbers such as square root of 2, e, pi, and so on. And finally, we'll be making use of the complex numbers, c, which aside from real numbers also include imaginary numbers, which use the imaginary unit I. So an example of a complex number would be 5 plus 3i. So I'll be assuming that you are already familiar with n through r, and hopefully you've already seen the complex numbers as well, but we'll briefly be defining them and giving a short review of them in what follows. We will define the complex number c to be the Cartesian product of two copies of the real numbers r. And so this is just ordered pairs a, b, where a and b are both real numbers. So an example of a complex number c would be 2 minus 3. Now, instead of using the ordered pair notation, we will write c, we will write it as a plus b times I, where I is the imaginary unit. So the I formally just serves as a dummy variable to allow us to distinguish which of the two numbers a and b is in the second position of the ordered pair. However, it'll be extremely useful to have this sum notation when we do arithmetic with the complex numbers. And so we call a the real part of the complex number, and we call b the imaginary part of the complex number. Now that we've defined what a complex number is, we can define a binary operation on the set of complex numbers, namely addition. Given two complex numbers a plus bi, and the second one c plus di, we can define their sum to be a new complex number a plus c plus b plus di. So what we've done here is we've taken the real parts of both of our starting numbers and added them together to get the real part of our resulting number. And we've taken the imaginary part of each of our starting numbers and added them together to give the imaginary part of the resulting number. Next, we can define multiplication. Given two complex numbers, a plus bi and c plus di, we can define their product by the following formula. So that's AC minus BD plus AD plus BC I. So this might seem kind of strange at first. We note that the real part of the first number shows up both in the real and the imaginary part of the resulting number, and the same goes for the imaginary part of our initial number. It also shows up in the real part and the imaginary part of the resulting number. We'll see soon that we don't really have to memorize this complicated formula. It's simply going to be a result of some easy rules of arithmetic. So I'll make some comments on the above definitions. So if we're given any real number x in R, we can identify it with a complex number x plus 0i in C. So this means that we have an embedding of the real numbers into the complex numbers, and so we have that the real numbers are a subset of the complex numbers. So next we'll have some abbreviated ways to write numbers that include a 0. So if we have a plus 0 times I, we'll just write this as a. And similarly, if we have 0 plus b I, we will just write that as bi. We now note that I squared, which if we write everything out is 0 plus 1 times I times 0 plus 1 times I. And if we apply the definition, what we get is 0 times 1 minus 1 times 1 plus 0 times 1 plus 1 times 0 I. And this is just equal to minus 1. So I squared is minus 1. And this fact allows us to derive the multiplication formula without having to remember the formula. Namely, we just need to remember that I squared is equal to minus 1. And then we can do arithmetic with complex numbers just as we would with real numbers. To illustrate this, I'll just show that if we have a plus bi and we multiply it by c plus di, we can just expand this as usual, treating I like a variable. So that gives ac plus a di plus bic plus bidi. And now we note that this term here is just bdi squared, which if we use the above and say that I squared is minus 1 is minus bd. And now we can collect the terms that contain I and those that don't. So the ones that don't contain I are AC minus BD. And the ones that contain I are AD plus BC. And we have that I, which we factor out to give the standard representation of the complex number. So if we compare what we obtained below, we see that this is exactly the same as what we got in the above definition. So in general, when we're doing arithmetic with complex numbers, we just need to remember that I squared is minus 1 and treat I as if it were a variable. So next we'll list some important properties of the complex numbers. So we'll let alpha, beta, and gamma be arbitrary complex numbers. Then we have that alpha plus beta is equals to beta plus alpha. And also alpha times beta is equals to beta times alpha. And this just says that addition and multiplication of complex numbers is commutative. Next, we have that alpha plus beta plus gamma, bracketed in this way, is equals to alpha plus beta plus gamma, bracketed in the other possible way. And similarly, alpha times beta times gamma is equals to alpha times beta times gamma. And this just says that the addition and multiplication of complex numbers is associative. Further, we have that lambda plus 0 is equal to lambda, and lambda times 1 is also equal to lambda. And this says that 0 is an additive unit, and 1 is the multiplicative unit. Finally, for every alpha in C, there exists a unique beta in C such that alpha plus beta is equals to 0. So this was the additive inverse of alpha. And similarly, for every non-zero alpha in C, there exists again a unique beta in C such that alpha times beta is 1. And this is the multiplicative inverse of alpha. So we'll denote the unique additive inverse of alpha just by minus alpha. And similarly, we'll denote the unique multiplicative inverse of alpha by alpha to the minus 1 power. It's worth noting that these properties don't just hold for the complex numbers, they also hold for the real numbers and the rational numbers. And this is because the real numbers, the rational numbers, and the complex numbers are all examples of fields. And these properties are pretty much just the axioms that we require of fields. So I'll be denoting a general field by this blackboard F. So this is a field. And a field is required to satisfy these properties. So it needs to be, has to have an addition and a multiplication that's commutative, associative, and has additive and multiplicative units, as well as inverses, where the only place to watch out is that we only require multiplicative inverses for non-zero elements. So if you don't know what a field is and you've never encountered one before, when I write F for a general field, you can just think of any one of the 3 examples over here. So just think of either the real numbers, the complex numbers, or the rational numbers. The last ingredient we'll need in order to define Rn and Cn are ordered lists, or n-tuples. So let me give the definition. First, let n be any natural number. An n-tuple is an ordered list of the form x1, x2, and so on up to xn. We write these lists in parentheses. Moreover, it's important that these lists are ordered, which means that 2 lists are equal precisely when they have the same length and all their elements are the same in the same order. So for n tuples x1, x2, up to xn, and an n tuple y1, y2 up to yn. These two are equal by definition when all the entries xi are equal to the entries yi for all I between 1 and n. So this means, for example, that x1 has to be equal to y1, and x2 has to be equal to y2, and so on, all the way up to xn and yn. Let's note that I allowed n to be an arbitrary natural number, so n could be 0. And in this case, when n is 0, the condition down here for two tuples to be equal is satisfied by default because there are no indexes I between 1 and n. So the only list of length 0 that we have is the empty list, which we will denote by just empty brackets. And so any two empty lists are equal. Let me give two examples that will help distinguish this notion of an n-tuple from that of a set. Let's consider the sets 3, 5, and the set 5, 3. Because set equality is defined by the elements that are in a set, these two sets are equal. So it doesn't matter in what order we write down the elements when we specify the set. However, on the contrary, if we have an ordered pair, that's just how we call the two tuples, are called pairs. If we have the ordered pair 3, 5, this is not equal to the ordered pair 5, 3, because in this case, x1 is not equal to y1, so 3 is not equal to 5. Similarly, sets don't respect repetition, so if we have the set that contains 4 listed twice, this is the same as the set that just contains 4, because the only element in this set is the number 4. However, on the contrary, if we have an ordered pair that contains 4, 4, this is not equal to the ordered pair that just has one entry of 4, because two n-tuples have to have the same length in order to be equal. We're now finally in a position to give the definition for Rn and Cn. So we'll do this a little more generally. We'll let F be any field. But we can think of the examples R or C if we want to be concrete. We also let n be a positive natural number. So in this case, we want to exclude 0. Then we define the set Fn to be the set of all ordered lists of length n with entries in F. So that's ordered list of the form x1, x2, and so on up to xn, where each xi is in F for all I between 1 and n. We call the entries coordinates. So for example, this would be the second coordinate. And in general, if we are in the ith entry, we will call it the ith coordinate. To make this more concrete, I'll give the following example, which we'll work with in what follows, namely R2. So here we set F to be R and N to be 2. And so by the definition above, this is just pairs xy, where x and y are real numbers. Note that by what we said before, this is the way we defined the complex numbers. However, we'd like to think about R2 conceptually in a different way, namely as points on the plane. So if we draw a coordinate system, we'd have 2 copies of R, and then a point would have an x and a y coordinate. So this would be the x coordinate, and here we'd have the y coordinate. This allows us to give a geometric interpretation of the pair xy as a vector. So we can draw an arrow from the origin to the point xy in the plane and think of this as an object that just has direction. And so each point in the plane corresponds to such a vector. And we'll see later how to add and scale these vectors in the plane. This brings us to addition in Fn. So given two elements in Fn, so x1, x2 up to xn, and y1, y2, and so on up to yn, we can define their sum to be x1 plus y1, comma x2 plus y2, and so on up to xn plus yn. So you see what we're doing is we're just taking the first two components and adding them, and this becomes the new first component of the sum. And we're taking the second component of each of the summands, and we get the second component of the sum when we add them together, and so forth. So this is called component-wise addition. To give an example, we can consider the vectors 3, 5, and -1, 2 in the space R2. So to add these, we apply the definition, and so we add together the first component, so that's 3 minus 1 is 2, and the second component is 5 plus 2 is 7. And that gives us our result. We can again give a geometric interpretation of this. So if we have our coordinate system, we can mark the first vector in red. So 3, 5 would be around here. And mark the second vector, -1, 2 in green, which would be approximately here. And now to add these geometrically, we have to line them up so that the end of one vector aligns with the beginning of the next. So here I'm going to transport the green vector in parallel so that it lines up with the end of the red vector. And now the resulting sum of these vectors is the vector that goes from the beginning of the first vector to the end of the second vector. So here should be 2, 7. The addition defined above satisfies some nice properties. So the first of which is that it is commutative. This means that if we have x and y in Fn, then x plus y is equal to y plus x. So we'll give a proof of this proposition. So we suppose that x, which is an element of Fn, is x1, x2, and so on up to xn. So we write out the more compact notation of x into its components x1 through xn. And similarly, we suppose that y is given by y1, y2, and so on up to yn. Then this allows us to write out this compact statement x plus y in terms of coordinates. So we have x1, x2 up to xn plus y1, y2 up to yn. So this equality is just expanding the more compact variable notation of having an x in Fn to its coordinate representation, which gives each of the coordinates in the base field f. And now we can apply the definition of addition, which is above, to get x1 plus y1, comma, x2 plus y2, and so on up to xn plus yn. And now we notice that the addition here in each component, so for example here, this is simply addition in the field f. And addition in a field is always commutative, so in each component we can switch the order in which the terms appear. So by the commutivity of addition in f, we get that the above expression equals y1 plus x1, comma, y2 plus x2, and so on up to yn plus xn. And again, this is just using the fact that addition in our base field f is commutative. Now we can just apply the definition of addition in reverse in order to separate out y and x again. So this gives y1, y2, and so on up to yn plus x1, comma, x2, and so on up to xn. So this is the definition of addition, but now used on the vector y1 plus x1, comma, y2 plus x2, and so on, in order to give the reverse ordering of the vectors we started with. And now we remember that y1, comma, y2, and so on is just y, and x1, comma, x2 up to xn is just x, and this means that this bottom expression is y plus x, and this is what we wanted to show. The addition we've just defined also has a neutral element, so it has a 0, and we can define the 0 in Fn to just be the list that contains only zeros. So we need to be careful here because we're using the same symbol for the 0, which is an element of the space Fn, while each of these zeros is an element of F. To see that this is indeed the neutral element with respect to addition in Fn, we can take a general element of Fn, so something like x1, x2, up to xn, and add it to the 0 element. So this contains n entries, which are all 0. And now by the definition of addition, this is just x1 plus 0, and so on up to xn plus 0. So we're adding 0 to each coordinate. And now because the zeros that are being added in each coordinate are the neutral elements in F, we have that this is equal to x1 and so on up to xn. So this shows that if we add the 0 element to an arbitrary element, we get back the arbitrary element unchanged. Continuing our example from earlier, the 0 element in R2 is just the ordered pair which contains zeros in each position. And geometrically, if we think about this as a vector, it would be a pretty boring vector because it's just a point in the origin, so it has no length and no direction. We also have additive inverses for addition in Fn. So let x equal some element x1, x2 up to xn, which is an element of Fn. Then minus x, so I'll define what minus x is. This is minus x1, comma, minus x2, and so on up to minus xn. And this is the unique additive inverse of x with respect to addition in Fn. So this means that x plus minus x is equal to 0. And here again, this 0 denotes the 0 element in Fn. So this is the list of length n that has only 0 entries. To see that minus x is indeed an additive inverse of x, we can again take an arbitrary element as x, so x1, x2 up to xn, and then we add its inverse, so that would be minus x1, minus x2, so on up to minus xn. And what we get, applying the definition of addition in Fn, is that we have x1 plus, and now we have minus x1, x2 plus minus x2, and so on up to xn plus minus xn. And these minus x1, minus x2, and so on, these are the additive inverses in f. And therefore, if we add x1 to its additive inverse minus x1 in f, what we get is 0. And we get 0 in all the coordinates. And of course, the list that contains only zeros is just the 0 in our space Fn. We can again give a geometric interpretation of this in R2. So if we have some point, say, let's call it 1, 2 in R2, then the inverse would be given by minus 1, minus 2. So if this is, let's call this x, then this would be minus x. And geometrically, if we have the vector 1, 2, then its inverse is just the vector that's mirrored along the origin. So that's minus 1, minus 2. And indeed, if we apply the addition, the geometric addition before, and line up the endpoint of the first vector, so of the red vector, with the starting point of the orange vector, what we get is indeed the 0 vector, because the 2 cancel out exactly. Finally, we can define a scalar multiplication on Fn. This means that given some lambda in our base field f and some element of Fn, so this would be x equals x1, x2, so on up to xn in Fn, then we define the scalar multiplication of lambda times x1, x2 up to xn to be equal to lambda x1, lambda x2, and so on up to lambda xn. So what we're doing here is we're multiplying each of the coordinates by the factor lambda. That's an element of our field. So x1 is being multiplied by lambda, and also x2 is being multiplied by lambda, and so on. And it's important to not get confused here. So we need to make sure that we understand that lambda is an element of the field f, not of Fn, while x is an element of Fn. So what we're doing is we're multiplying two objects that live in different universes. But we do this in such a way that we get, again, an object that lives in Fn. To illustrate this in R2, if we have, say, 3, 5, which is an element of R2, and then we take a scalar, so we could take, for example, 2, which needs to be in the base field, so 2 is an element of R. So here we've substituted f for R, so we have and 2 for n. So we take lambda equals 2, and we take the x equals to 3, 5. Then what we obtain is that 2 times 3, 5 is equals to 2 times 3, 2 times 5, which is nothing else than 6, 10. Geometrically, if we have our vector 3, 5 somewhere around here, then the result of multiplying 3, 5 by the scalar 2 is the vector 6, 10, which is roughly up here. And so we see that this just corresponds to stretching out our original vector by a factor of 2. So to give another example of other things that can happen, so if we multiply our vector 3, 5 by half, then what we get is 3 halves, 5 halves, and this would be a vector that is half as long. So the idea of scaling the vector is correct. Then there's a third case which is when we have negative numbers. So let's say we have -1 times 3, 5. This just corresponds to the additive inverse, -3 minus 5. And we've already seen before that this is just reflection along the origin. So if we have a negative number, we still scale the vector, but we also reflect it in the other direction along the origin. We've covered a lot of ground, so let's review what we've seen so far. First, we defined the complex numbers and gave some of their properties. So we defined the set of complex numbers as R cross R, which is the set of ordered pairs AB, where A and B are elements of the real numbers R. And we wrote an element of C as A plus B times the imaginary unit I. Using this definition of complex numbers, we defined an addition where we just add the real parts and the imaginary parts separately of the corresponding complex numbers. And we also defined a multiplication that had a fairly complicated formula, but we saw that we don't have to learn this formula by heart. We can just treat I as a variable and remember that I squared is -1, and then we can always derive the multiplication formula for ourselves. Then we saw that the complex numbers with addition and multiplication defined in this way have nice properties. In particular, they form a field F, and we introduced the notation of this blackboard F for a general field, but we can always think of this F as representing either the real numbers R or the complex numbers C if we wish to do so. Then we went on to construct Rn and Cn, and we gave a general definition of Fn. So this construction works for any field F, and Fn is defined to be the set of ordered n tuples, x1 through xn, where each entry is an element of F. Next, we defined an addition on this set Fn by just adding each of the coordinates independently. So this is a component-wise addition. Finally, we defined a scalar multiplication, which allows us to multiply elements in Fn by scalars, and these scalars, they live in the base field F. So this was important to remember. And the scalar multiplication works as follows. We just multiply each of the coordinates by the scalar lambda. In the next video, we will give the definition of a vector space, and we will show that Fn is basically the prototypical example of a vector space. And hopefully this will serve to clarify why we care about the operations that we've defined in this video. So I hope to see you then.